Welcome to the Day Zero Intermediate Prerequisites. Previously, we saw about the beginner prerequisites, in which we saw a detailed introduction to NLP, which covers key components of NLP, common tasks in NLP, challenges in NLP, applications of NLP, followed by which we saw how the NLP pipeline works, after which we saw a detailed explanation on the methods which are present in text preprocessing, where for regex alone we gave some special importance because that is even widely used nowadays, even after LLM has come into the picture. After which we moved on to embeddings, which are nothing but the vector representations of the text, where this vector representation basically captures the semantic relationship between those words. We saw the types or embedding methods which can be used. There is one embedding method which I didn't cover here, and that embedding method is something which we'll see later because that is advanced, and those concepts can be discussed only after I discuss about transformers. And then finally we ended up with an introduction to NLP with machine learning, where we trained our own naive Bayes sentiment analysis classifier. So that was about the beginner prerequisites. Now, in intermediate prerequisites itself, it has been made as two parts. So the first part would be about deep learning on an overall aspect, like what are the aspects which are there while we train a neural network, and so on and so forth, like that. And the part 2 will be focused on NLP oriented networks, which is RNN. So we'll be seeing about these networks in detail later in this video. So with that being said, let's jump into the video by starting up with an introduction to deep learning, answering the questions of what, why, when, and how. What is deep learning? Deep learning is a subset of machine learning that uses artificial neural networks with multiple layers to model and solve complex problems. Please highlight the word to model. And why is that? I'll say in a minute. So it is inspired by the structure and function of the human brain. Now, what is the difference between machine learning and deep learning is that machine learning algorithms have their own predefined mathematics, and what they will do is they'll try to find the best value for a variable which is already defined in the equation, which means it is expected that your data has a linear relationship in it. Okay? But that is not the case with deep learning. How much ever complex relationship is there, how much ever polynomials it involves, doesn't matter, because these neural networks will be able to find those relationships by themselves. So that is what is deep learning. Why should we use deep learning? Automatic feature extraction, because deep learning has the capability to automatically learn features from data rather than a lot of feature engineering, which will be usually done when we work with machine learning models. Scalability, performance usually improves with larger models and more data, so it is highly scalable. Versatility, deep learning networks have a wide range of applications from text to image to speech and so on and so forth, even playing games. And it provides state-of-the-art performance in whatever domains we see. It achieves the top results. Often even it surpasses human level performance. So that is why we need to use deep learning. When do we need to use deep learning? When there is large amounts of data, we can use deep learning, because deep learning, it thrives on big data. It loves having big amounts of data. When you have complex problem, like I said, if there is a high non-linearity in your data, or there is high dimensions and you want to find a variable with the help of machine learning, that is going to be hard. So at that time, you can use deep learning. When you have unstructured data, like I said, image, audio, and text, you can use deep learning. For time series data, you can use a specific variant of neural network, which is RNN LSTM, which we'll see in detail in the later part. And then in autonomous systems also, you can use. How deep learning works, the pipeline, basically. So first you will collect the data, and then you'll make your own neural network architecture. So that is your model building phase. And then model training phase, what we'll do is we'll do a forward propagation, calculate the loss, and then we'll update the weights in the backward propagation phase. These are just introduction. Don't worry. All of these will be explained each and every concept in detail later in this video. Evaluation, testing the model on unseen data, and then once you have evaluated, you can just deploy it, and that is what is using the trained model for predictions on new data. So what are the advantages of deep learning over machine learning? Feature learning. ML often requires feature engineering, but DL can do that by themselves. Performance with large data. Machine learning has its plateau. Plateau is something like, your curve goes like this. Let's say your learning curve is this, okay? Higher the better. Machine learning will go like this and then it will go like this, okay? But deep learning will always go like this. It always thrives with large data. Handling unstructured data. Machine learning can't do that, but deep learning can. Scalability. Though machine learning models are faster, it is not highly scalable for complex use cases, but you can easily scale your deep learning models for complex use cases by just adding layers. Transfer learning. Nowadays, if you see LLMs, we are not training the LLM, we are transfer learning. We are fine-tuning the LLM. It has some knowledge to it. We are just adding some knowledge on top of it. That is easier with the case of deep learning, but with machine learning, it is very limited. So to say, it is close to impossible. And then we have parallel processing, which is something you can do with deep learning, but not with machine learning. However, deep learning has some disadvantages as well. Like I said, it requires large amount of data and it is computationally intensive. It is not as interpretable as machine learning, because with machine learning, you have equations defined prior, but with deep learning, it will try to identify the equation by themselves, which means it is going to be a black box. And if you don't regularize your network and normalize your network well, it will be prone to overfitting. So depending on the problem you are facing and data available and computational resources, you can either go for machine learning or deep learning. Now, with that being said, how will you create your deep learning neural network architectures? There comes our savior, PyTorch. PyTorch, if you see, it is an open source machine learning library or deep learning library. Like I said, deep learning is a subset of machine learning. It is a library which has been developed by Facebook's AI research lab. It was created by Facebook AI, but now PyTorch is a separate organization. It provides a flexible and efficient platform for building and training neural networks, making it a popular choice among researchers and developers in the field of deep learning. There is another competitor as well, which is TensorFlow, but it is more rigid. But PyTorch is more flexible. Why is that? First, it allows you to use dynamic computation graph. The model architectures will be very flexible and easier for debugging. Dynamic computation graph is nothing but, your forward and backward computation will be, a form of graph where the gradients all will be stored. Okay. So that is your dynamic computation graph. Pythonic interface, the most important aspect as far as the developer is concerned. It provides a natural interface that aligns with Python programming practices. If you are a Python developer, you will be very well versed with using classes, and PyTorch expects you to use classes. That is not the case with TensorFlow. GPU acceleration. PyTorch provides built-in support for CUDA to be used for training your neural networks. Autograph system, which will automatically compute the gradient while you do backpropagation. And it has a variety of tools for CV, NLP, and reinforcement learning. These are some of the key features and reasons why developers and researchers in the field of deep learning prefer PyTorch over other frameworks, with TensorFlow being the second most popular framework right now. So PyTorch has many functionality, and here it has broadly been categorized into some areas. One is tensor operations. So at the core, PyTorch tensors are multidimensional arrays, as like NumPy arrays. So if you are wondering NumPy array, what is it? It is just, normal list, but, it is of NumPy, which will allow you to do complex mathematical calculations. So this now Torch tensors will allow you to run it on GPUs. Okay, so let's say I have an X tensor which is 1, 2, 3, and then Y tensor where I'm calling torch.rand, and the size is 3 cross 3. Okay, so 3 cross 3 random tensor will be generated, something like this. So you will have your data like this. Okay, that is what is 3 cross 3. So how you can identify this? When you call tensor.shape, you will be able to see the tensor shape. Okay, so I'll also print that, print y dot shape. Okay, and then we'll also print z. Along with that, we'll also print w, which is just multiplying the same array on itself. So here you can see the tensor shape is 3 cross 3, and here is basically a reset where this is how it has been added. Okay, so with 1, 2, 3 being here, and if you print y, you'll be able to understand what is the value of y. Here you can see it is 0.94, 0.60, and 0.95. With 1 being added, everything will become 1.1.1. Same will be 2.3 points, and so on and so forth. Okay, that is your basic tensor operations, and all will be under Torch. Okay, and in Torch there is something called autograd, which will automatically compute your gradients, and that is why I said the computation graph is very flexible. So here all you need to do is just set requires grad is equal to true, and what will happen is if I do x is equal to torch.ones of 2 cross 2, so it will generate a 2 cross 2 matrix, and then we'll add 2 to those variables. Okay, and once that is done, we'll multiply y by y, and then we'll multiply it by 3. Okay, so if I do this, here you can see I've got z.mean, and if I call backward, and then finally if I print the x gradient, this is what is my gradient. But previously if you see x, it has been 1, 1, 1, 1. This is the value of the gradients, not the value of x. All right, so that is autograd. So autograd is basically your differentiation, which will be used for loss optimization, which is in backpropagation. Okay, so there is an important module which is torch.nn module or neural network module, when we say it as an abbreviated form. So the PyTorch provides a high-level API for building neural networks through torch.nn module, and here is how you can implement a simple torch neural networks. So torch.nn as nn, you will import it, you will create a class or whatever you want, and you will inherit this nn.module. First, in init.self, you need to override the parent class. So you'll call super of simplenet self dot dunder init. So here we are taking 2 fully connected layers. So what are those fully connected layers? It is nothing but like those are ANN basically. Okay, and what it has is a number in represented in dimension 10 will be represented in dimension 5, but it will be learning out of those. Okay, that is how it happens with linear layers. So here if I print the model, this is how the model is. Okay, and how the forward will happen here, your ReLU activation function will be applied on fully connected layer 1 output, and then that output will be sent as an input to fully connected layer 2, which will provide the X output. Okay, so that is your neural network modules. And with data loading and processing, it is very important to know about the tools provided for data loading and processing. So the first tool is Torch Dataset. It will allow you to make a dataset of your own, and then data loader, which will load the data. Okay, so this is how the structure is. Don't worry, we'll see about this in detail, but just to say, these components will work together to provide a comprehensive framework which will help you to develop, train, deploy your deep learning models with ease. And PyTorch design has been emphasizing on ease of use, flexibility, performance, and then it is very powerful for both research and production environment. Okay, so those are the PyTorch functionalities, key functionalities. Okay, but there are some other functionalities as well, where, like for example, torch.optim, which contains the optimizers, which we'll see later. Okay, now jumping on to the PyTorch dataset and DataLoader. So what is PyTorch dataset? In PyTorch, the dataset is an abstract class which is representing your dataset. Any custom dataset you create should inherit this dataset class, and it will override these two methods. One is dunderLearn, and then another one is dunderGetItem. So the dunderLearn will say, like, the size of the dataset is this much, and dunderGetItem, what it will do is, once you have an index passed, the data will be returned. Okay, that is what is getItem. So if you have any kind of pre-processing to be done on a raw data, those will be done in this getItem section. Okay, so for example, I want to do something like this. It will be done in dunderGetItem. So the custom dataset class will inherit the dataset class, and here in init function, it takes two values. It is data and labels. So the length of the data is going to be length of self.data. And in getItem, what we are going to do is we are going to provide the data at an index. Okay, that is what is the purpose of dataset. A dataset or a data value at a specific index in the dataset is obtained via getItem. Okay, so that is what happens in Torch dataset. But only dataset is not enough. Okay, it is not of any use. What we use is DataLoader. So one of the most important advantages of PyTorch is that it supports multiprocessing, and for using multiprocessing, you need to use DataLoader. What it will do is it will iterate over the dataset while it supports automatic batching, shuffling, multiprocessing, all it will support. Okay, these are the three main features of a DataLoader. So if I have a custom dataset being called with A, B, and 1, 2, I'll say my batch size is 1, and I'll set shuffle to true. Num workers you can set to how much ever you want. I don't have a lot of processors left in my system, force, so I'm setting it to 0 so that it will run in single thread, but you can run in multi-threads as well. So here you can see A is printed because that is the first one, and then the label is also printed. Okay, so you can see, right? So why A and B are coming one, not in a sequence. It was A, B, A, and then another time A and then B. So why it happens is because we set shuffle to true. Okay. So what this DataLoader will do is this will provide the batch of inputs to the model. Okay. But this will support multi-GPU, multi-processing and all, so making your training more efficient. So basically the idea is that you will create a data set which will represent your data set basically. So it is not just a data frame, it will be a torch data set, and that will be loaded with the help of a DataLoader into the model. So that is what is all about PyTorch dataset and DataLoader. Now let's see about neural networks. What are neural networks? Neural networks are computational models which are inspired by human brain structure and function, because researchers wanted to know, replicate the functionalities of human brain, because that would be the real step towards artificial intelligence rather than with a pre-computed equation. So that is what is neural networks all about. It consists of interconnected nodes or else neurons, because neurons is the smallest functional unit of a neural network, and neurons is the most smallest functional unit of a human nervous system. Okay, so like I said, cliche, right? They wanted to replicate the human brain. So these neural networks have interconnected neurons which are organized in layers, and these are designed to recognize patterns and solve complex problems. So that is what is neural network. So why should you use neural network? So whatever we said as a reason for using deep learning, it will apply to neural network, because neural network is the reason for which deep learning became popular. Pattern recognition, it is excellent at identifying complex patterns in data because it computes the relationship equation by itself. And then adaptability, it can learn and improve from experience. Generalization, it can make accurate predictions from, like experience on unseen data. Non-linearity, like I said, it can model. It means it can create. That is what is the stylish way to say, can model complex non-linear relationship. And parallel processing, that is also allowed. And how do neural networks work? So once you get an initial data, it will be sent to the input layer, and it will receive the initial data, will be passed to the hidden layers where the real magic happens, where all the calculations are done with the help of weighted connections, and then the output layer will provide the final output. Here in between, we'll use a lot of things like activation functions. We are training it, and we'll do backward propagation, which is using optimizer and all. Okay, so that we'll see later. But the process is that you'll have a forward propagation, and how that will happen. Input layer will obtain your input, and hidden layer will do the mathematical calculation and say this could probably be your output, and the output layer will say this is my final result. So that is what is neural network. Now this is how you can create a simple perceptron from scratch with the help of NumPy. So first, we are just creating a simple class known as perceptron, where we are saying our input size and then the rate at which the model needs to learn. Learning rate is a control parameter where it will say at what rate you want to learn. And don't worry, we'll see about learning rate later in detail in the backward propagation section. So the weights are going to be np.random.rand, we are just randomly initializing weights and biases, and the learning rate is already obtained here. Okay. And for activation function, we have a function called activate, and predict will be your output gate basically. Okay. So how basically a perceptron works, this is how it works. And now you won't be able to understand this. Okay. I'll say that now itself. Now you won't be able to understand this. When you will be able to understand this? Once I teach about forward propagation and backward propagation. Okay. Let's see that now. Once we see about the different architectures of neural network, variety of neural network architectures which are available. First is the most basic type, which is artificial neural network, which will have one input layer, one output layer, and one or more hidden layers. The most suitable use cases would be classification, regression, pattern recognition, where you have a closer to structured data. Pros is that it is versatile, it can approximate any function basically, and the cons is that it will structure with spatial or temporal data. Spatial is nothing but the geographic data, and temporal data is the data which involves time as an aspect inside that. So CNNs are specialized for processing grid-like data such as images. Okay, so the key components here are convolution layers, pooling layers, and fully connected layers. Fully connected layers are, one single perceptron, and then, you have replicated it as a layer. Okay, that is what is fully connected layer. Dense layer, we say it. So the use cases will be mostly involving vision related things, computer vision tasks like object detection, image classification, and so on and so forth. It will be very efficient for spatial data. So when there is geography related, images, it will be very good. And the parameter sharing thing, which is there in pooling, it will reduce overfitting. But the cons is that when there is non-spatial data, like for example, temporal data, it will struggle. There came RNN to solve the issues in CNN. So if you see, ANN had issues which was solved by CNN, and CNN had issues which was solved by RNN. But there are things which CNN can do, but RNN can't do. Okay, because RNN had focused on one specific issue which was there in CNN. Okay, so RNNs are designed to work with sequential data. The key feature is that the loop in the network, which will be there, it will allow you to have information being persisted towards all the time. There are variants of this network like LSTM, GRU and all. The use cases is mostly related to sequential data, which is natural language processing related task, time series related task, and so on and so forth. Pros is that it can handle variable sequence length data sets, maintaining temporal information, and cons is that it is very difficult to train due to vanishing and exploding gradient. Okay, so these are the type of neural network. Before going into these, which is creating a PyTorch simple ANN, let's see in detail about forward propagation and backward propagation, and then we'll move on to creating a PyTorch simple PyTorch ANN. Okay, so for forward and backward propagation, I have provided a separate file, markdown file, because there is a lot of mathematics involved in backward and forward propagation. So to explain that, it is better to have a separate file. That is what I felt and I have provided here. So let's start with the forward and backward propagation now. In neural networks, forward propagation and backward propagation are the two most fundamental processes in the training procedure. Forward propagation is the process of passing the data, input data through the network layers, where you'll calculate the output and you'll compute the loss by comparing it with the actual target. Basically, what you'll do is there will be an input layer and you'll provide your input there, and then all the calculation will happen in the hidden layer and then will be sent to the output layer, and then the output will provide an output which is a prediction, and that prediction will be compared with the actual target, and that will provide you the loss, right? So that is the forward propagation. So now I've said it in an overview, but how this actually works, let's see as a step by step with a mathematical example, right? The input layer. What happens in the input layer? The process starts by feeding the input data to the network. That's all. Okay. Just providing the input data to the network. That is what happens in the input layer. Let's say we have two features. Okay. Two features is like two dimension. Okay. One is x1, another one is x2, and your target is y. And here y is equal to 1. x1 is equal to 1 and x2 is equal to 1. These are the features. Okay. Now what you will do is first you will calculate the weighted sum, or else it is also known as linear transformation. Each input is multiplied by a corresponding weight and it is summed. So if you all know what is linear regression, the formula is y is equal to mx plus c. Okay. Here the linear transformation equation would be y is equal to w transpose x plus b. There m will be your slope and c will be your constant, right? So here it is replaced by weights and bias. Okay. And by the way, we'll update those weights and biases that is there. Okay. But these are the parameters which are responsible for neural networks to learn. For neural networks to learn, we'll be updating the weights and biases. So here you can see that each input is multiplied by a corresponding weight and sum. Along with that, we'll add a bias term as well, because at times there might be a possibility that you might face 0 when you multiply, right? So at that time, now let's take an example that we have two neurons, all right? The two neurons will have weights for each, and these are in hidden layers. Okay. So the weights for the first neuron is W1 and W2, which is 0.1 and 0.6. And weights for the second neuron is 0.5 and 0.7. All right. Now here you have bias as well, which is B1 and B2. And the values are 0.2 and 0.3. Okay. So why is there two weights for one neuron? Let's see that. Here we have a sample neural network which has two input neurons. Like I said, we have two inputs, right? 1 and 2 as x1 and x2. Two hidden layers, neurons. Actually, there is only one hidden layer, as you can see here. And there is two neurons in there. Okay, that is why the representation is input layer belongs to a layer which has two neurons. hidden layer also belongs to 2 neurons, and output layer has 1 neuron. That is what is our architecture, and this is how the neural network will look like. Okay, now let me tell how those weights came into the picture. Here you can see there is a red line, there is a tainted blue line, and then there is another red line, there is another blue line, right? So these lines contain the weights. Okay, these lines contain the weights, and there is a bias as well. Okay, similarly here also, if you see, there are 2 weights and there will be 1 bias. Okay, so this is how a neural network will look like. So here you can see, if I increase the number, say it is like this, and the hidden neurons goes like this, I have another layer, let's say, and here you can see now this is a bigger neural network. As you can see, the connections are pretty huge, and yeah, here you can see there are pretty good connections between everything. All right, so this is how basically a neural network looks like and works like in a forward propagation. Now let's continue with the explanation. So we compute the weighted sum. How that happens? In the neuron 1, we'll calculate it as x into w plus x2 into w plus b1. Like I said, the w transpose x plus b, right? This is how it happens. So if I calculate, let's say the weights initially is initialized as, like, weights, you can't control it. You will just randomly initialize it following some methods like hey uniform, hey normal, Xavier uniform, like that. Okay, so the output would be of, like, the first hidden layer would be 1 into 0.4 plus 2 into 0.6 plus 0.2, which will be 0.4 plus 1.2 plus 0.2, which is equal to 1.8. Now Z2 will become 1 into 0.5 plus 2 into 0.7 plus 0.3, which will become 2.2. Okay, so this is how the weighted sum is. Now what happens is, in a forward propagation, in each neuron, first the weighted sum will be calculated, and after that, that output will be applied with an activation function, because that is what is used to capture the nonlinearity. Okay, so the output of each neuron is passed through an activation function. Example, ReLU, Sigmoid, Tanh. We'll see these in detail later. What the idea is, that is, it is to introduce the nonlinearity. The ReLU activation function mathematical formula is max of 0 comma x. Okay, so let's say there is a neuron 1, the A1, which is the output of neuron 1 itself. Let's say, like, there is a neuron, and the first half will be weighted sum, second half will be activation function output. So the activation function output is technically the neuron output. So the neuron output of first neuron is 0, max of 0 comma 1.8, which is 1.8, and then max of 0 comma 2.2, which is 2.2. That is what is the activation function, or the output of the hidden layer 1. Okay, now you have an output of 1.8 and 2.2. What happens now is, you have an output layer, and like I showed in the diagram, there will be only 2 weights following. Okay, so there is 2 weights here, 0.8 and 0.9, along with 1 bias. So what happens here is, we will multiply with 1.8 and 0.8 together, and 2.2 and 0.9 together, plus 0.1. Okay, finally your output layer output is 3.52, but what was our expected output, which is 1.1. Okay, that is our expected output. Now you might wonder, okay, there is input, but there is output which is not at all related. How we'll adapt that? That is why we have the process of loss calculation and followed by backpropagation, where what we'll do is, we'll change the values of this weight 1 and weight 2 such that this output value of 3.52 will become closer to 1. Okay, now let's see how those happens. Loss calculation is the final step in forward propagation, and how it happens is, you have a true target, which is your output or your expected output, and then you also have the model output, which we'll say, like, y output. Common loss functions used are mean squared error, cross-entropy loss, and there is hinge loss, binary cross-entropy loss and all. But right now, let's see the most simplest loss function, which is mean squared error. Mean squared error is, the formula is, we'll compute the error and then we'll square it and then we'll divide by 2. Okay. So the y output is 3.52, y true is 1. So 1 by 2 of 2.52, the whole square will be 3.1752. Okay. So that is the loss right now. Now you need to reduce this loss, and that's where backpropagation, which is the second phase or probably the more important phase in deep learning, comes into the picture, which involves calculating the gradient of the loss function with respect to each weight in the network and then updating those weights using an optimization algorithm. For example, that is gradient descent. How step by step it happens. First, we'll compute the gradients for loss, and the formula is partial derivatives. We'll use partial derivatives here. Dou loss by dou output. So it will be z output minus y true. Okay, dou loss by dou output is z output minus y true, and the value would be 2.52. Now you have dou loss by dou output. Okay. Now what you will do is you'll calculate the gradient at that output layer. Okay, now you have calculated the gradient for loss alone. Now you'll calculate the gradient for the output layer itself. So how that happens is, with respect to every weight, we'll do that. Okay, dou loss by dou weight phi is equal to, if you see the weight phi, it has been constituted with the help of activation function of first neuron's output. So we'll take that only. Okay, in backpropagation, everything happens in reverse. So activation function 1 output into dou loss by dou output, which is 1.8 into 2.52, which is equal to 4.536. So similarly, you will calculate it for dou loss by dou w6, which is 5.544, and then we also calculated it for bias, because bias doesn't have value already. It is just a constant value. So here, for partial derivative, we'll just consider the value of dou loss by dou output itself. Now we'll calculate the backpropagation at the hidden layer. Now to backpropagate the error at the hidden layer, you should use a chain rule. Okay, the error signal at each hidden neuron is a product of the derivative of activation function and the error propagated from the output layer. So what does that mean? These values will be propagated to here as well, along with the differentiation of the output of activation function. Okay, so the activation function is ReLU, and if you differentiate that, if the asset is greater than 0, it will be 1 and 0 otherwise. Okay, you will never face 0 a lot of times. There are some times, and we'll see about that later, but it will be always 1 mostly. Here if you see everything is 1, so we need not worry about multiplying it with some 1 or 0. All we need to do is multiply the weights of 5 and 6 with this output we obtain. Okay, because this is gonna be the value which will impact the gradients at the hidden layer. So it is going to be 0.8 into 2.52, which is equal to 2.016, 2.268. Okay, now these are the error at neuron 1 and neuron 2. Okay, that is why we multiply the weights. Now what is the gradient there? So if you want to calculate the error, right, you will use the weights values of the layer plus 1. Okay, let's put that way. Let's say if it's a hidden layer and there is one output layer and then one input layer. Okay, so to calculate the output or the gradient at the hidden layer, you will use the error at output layer, and then you will calculate the gradients with the help of inputs which we obtained previously. Okay, so the calculation would be dou loss by dou w1 into dou loss by dou z1, which is 2.016, and 4.032 in place of weight 2. And then bias 1 will be 2.016. There also, if you see, we calculated it for weight 5 and weight 6, right? Now we are calculating it for weight 1 and weight 2 because that is the first neuron, and second neuron is 2.268 and 4.536. And here, since now we have the values of gradients, we can update those values. So if I want to update a weight 1, what we will do is we'll have a learning rate, like I said right previously, the rate at which you want the model to learn. Slower the better, okay? Slow and steady wins the race is the proverb, and that works for deep learning, okay? So the formula would be, let's say this is weight new, okay? Because you are updating that weight, right? Weight new is equal to weight old minus learning rate into dou loss by dou w, which we calculated already, okay? So it is going to be 0.4 because that was the weight 1. So you can see, right? Weight 1 is 0.4 into minus 0.01 into 2.016, which is 0.37. Now, if you see, the weight has been reduced from 0.4 to 0.37. So similarly, from 0.6, it has been reduced to 0.55. Similarly, it will reduce or increase based on, like how you want it to be. Okay, this process will be repeated for each training example across multiple epochs until the network will converge. Okay, so in that way, your loss will become minimal. This is how basically the deep learning procedure happens. In this, as a summary, forward propagation will involve weighted sum, applying activation, calculating output, and then loss. From that loss, you'll start backpropagating the gradients with respect to weights and biases, and then you'll update them with the help of gradient descent. So here it was said as a simple step that it is update of weights and bias, which uses gradient descent. Okay, gradient descent is an iterative optimization algorithm that is used to minimize a loss by adjusting the model parameter, which is weights and biases. The main idea is to move towards minimum loss function by taking small steps in the opposite direction of the gradient of the loss. What is meant by that? Let me show you. Here is a sample curve of gradient descent. Okay, if I stay here you can see the main idea is to move towards the minimum, taking small steps in the opposite direction of the gradient, which is slope of the loss with respect to its parameters. Here you can see, let's say initial weight is here, okay, but the loss will be 0 at here, and this place is known as global minima. Okay, at real time the curve won't be looking like this. It will be like it will be like this and this. Your challenge would be there will be a lot of local minima here like this, but there will be a global minima here you need to attain here. Okay, that will be a challenge. We'll see about that later. Okay, now we will have those gradients, right? We already calculated those are the gradients which are here. Now your weights are here. You need to take a step by moving from here to here, and then here to here, here to here, here to here, here to here. Finally, you will achieve the minimum cost at 0, like close to 0. You will never reach 0, but you will achieve close to 0 performance. Okay, so this is how the gradient descent curve works. Okay, now let's see the mathematical explanation, because we saw a graphical explanation right now. What you'll do first, you'll compute the gradients. The gradient of the loss function with respect to each parameter, which we did before. Here you can see, right? This partial derivative we calculated, right? Those will provide the gradient. For a weight W, the gradient will be dou loss with respect to dou W. If it is in the output layer, yes, it will be directly impacted by loss. But if it is in hidden layer, you need to propagate the impact of loss from those output layer to the hidden layer. That is what we did here. Okay, first we took the output and then we impacted it at the output layer, and then we backpropagated it to the hidden layer with the output of these layers, right? So dou loss alone will be considered, but those output also impacted it, right? So we'll consider those outputs as well. So here is a sample. Okay, let's say my weight is 0.5, and then my gradient of dou loss by dou W is 0.2, and the learning rate is 0.01. So 0.5 minus 0.01 into 0.2 will be 0.498. Now it is a bit adjusted. Now it will come closer. Okay, that is the idea of gradient descent. This is how you will update the parameters. For bias also, it is the same. Bias name will be equal to bias old minus learning rate into dou loss by dou b. Dou b is dou bias, right? Partial derivative calculated with respect to loss for bias. This is how gradient descent works. And there are algorithms like batch gradient descent, stochastic gradient descent, mini batch gradient descent, and so on and so forth. These are the basic optimization algorithm. There are lots of optimizers which has come into the picture, which we'll see in the optimizer section. Okay, but this is how forward and backward propagation works. Yes, I explained it very theoretically, and like I said, some explanation with the diagram that is for simple. So like just try to put some time into this document, and then you'll be able to get a hang of what is happening. Okay, so as a summary, what happens in forward propagation is it is a process of computing the output of a neural network for a given input. Why you should do that? You should do that to make the predictions and compute the loss. How you'll do that? It is by sequentially applying each layer's operation to the input data. Backpropagation is the process of computing the gradients of the loss with respect to the network parameters. And why you'll do that? It is to adjust the model parameters, which are the weights and biases, to minimize the loss. And for this, you'll use the chain rule. Okay, chain rule is what we did. Like we did it separate, and then we multiplied it. But like at real time, what they will show is like it will be a single equation. By applying the chain rule of calculus, you'll propagate the gradients backwards through the network. Okay, this is what happens in forward and backward propagation. Now that we know that, let's see the theory behind the simple RNN network, and then we'll code that. Okay, a multi-layer RNN network, also known as a feed-forward neural network, consists of multiple layers of neurons. I showed you, right? There is multiple hidden layers when I showed you that. So there will be one input layer and output layer that is constant. But hidden layer and is like number of times you can just replicate it. More the number, better the output. And then back propagation, just now we saw, right? It is the process of adjusting the weight. Now let's see how you can code this. Okay, this will be a sample code. Okay, don't worry, we'll train that. PyTorch provides a high-level API for creating neural networks through torch.nn module. So for that, what you need to do? You need to first define a class that inherits the nn.module, define all your layers which you'll use in the dunder init method, and then implement the forward method, which is just what we saw as forward propagation, taking the output of first calculating the weighted sum, and then applying the activation function, provide that output to the next layer, calculate the weighted sum, and if there is an activation function, calculate that, and so on and so forth till output. That is how we did the forward propagation theory, right? So that's how we'll do it in forward as well here. Let's take a simple example that we have two layers, okay? And there is one activation function for the first layer alone, okay? So the dimension here would be 10 cross 20 and 20 cross 2. Now you'll wonder, 10 cross 20 and 20 cross 2, how is this thing? So what happens is, actually you'll have three layers to look like. Okay, there will be 10 neurons at first, which will be projected to 20 neurons here, and then those will be projected to 2 neurons. Okay, so if I had it like 2 to 1, this will be the same network which we discussed right now. Okay, so here we have the layers being initialized as linear layers. Those layers which we said about is linear layer, simple linear layer. And then the activation function will be also there in NN module itself, NN module. So we'll call ReLU activation function. And here if you see, once we get the input, we are passing it through the layer 1, which will provide you Z1, okay? And then that Z1 will be provided to ReLU, which will be your O1, and O1 is provided to your layer 2, which is to your output, and then that will provide your output. Okay, so this is how a neural network is defined. And here you can see there are some common layers. There is linear layer, which is also known as fully connected layers. That is what is used in ANN. And linear layer is generally used in any network because fully connected layer is the only layer which has the capability to extract the information which is already there by expanding it and contracting it. Like the equation it calculates, it is very versatile to adapt it to any domain. There is 2D convolution layer which is used for images. There is RNN LSTM GRU for recurrent layers, which we'll see later. And batch normalization is there, and then dropout is also there. Dropout is there because you don't want your model to memorize things, right? So at that time, what we'll do is, it is a normalization method where what you will do is you will just drop some of the neurons. Let's say you have 10 neurons in one layer. You have provided the probability of dropout as 0.2. What it will do is it will keep 8 neurons and 2 neurons output will not even be considered, considering that is a dropout neuron. Batch normalization is the process of normalizing the values or inputs which are provided to that layer. Okay, that is batch normalization. Activation function, there are common activation function like ReLU, Sigmoid, Tanh, softmax, and for loss, MSE, Cross-Entropy, BCE loss, an optimizer, stochastic gradient descent, which we saw already, a variant of gradient descent, and then there is ADAM, RMS prop and all. Okay, so a training loop example will look like this. First, you will get the loss function. You'll initialize your optimizer. So what you will do is, you'll go through the number of epochs. For each epoch, you'll go through the inputs which are there in the data loader. You'll get the model outputs. You'll calculate the loss. You'll first set the optimizer to 0 gradient. Optimizer is nothing but the gradient descent algorithm which we saw. Okay, and then you'll call the loss.backward. And the good thing is the loss.backward will compute all those partial derivatives we spoke about. Okay, so the backward propagation will be done and the model weights would have been updated. Now you'll call the optimizer.step function, which will complete that procedure. Okay, backward propagation will calculate those gradients and the updation will be done with the help of optimizer.step. This is how a basic training loop will happen. Okay, now we saw a simple code explanation. Now let's train a simple RNN network itself. Okay, here I have imported Torch. From torch.neural network modules, I have imported it as neural network module, and then we have imported torch.optimizer as optimizer. From data utils, we have taken Dataset and DataLoader. From sklearn.model selection, train test split is called, and then NumPy is imported as NP. You have a random dataset class. Okay, like the class, why I named it as random dataset is because I'm just generating random values for X and Y. Here the thing is, there is only one input feature and one output feature. Based on this input feature, it should say an output. Okay, that is what is the expectation here. So I've just provided as X and Y, where len will be X, len of self.x, and when you call an index, it will provide the value of X at that index and value of Y at that index. Okay, the neural network we already saw there, right? That is what is the neural network here. And then we have 1000 samples which we need with input sizes 2. So why it is input sizes 2? We need to provide it to a layer which has 2 neurons as hidden size, sorry, input size. Okay, and then we have the number of classes which is output as 2. Okay, that's why we keep it output size as 2. Hidden size doesn't matter. Okay, so here it will be 1000 cross 2, and then here it will be 0, 2, 1000. This is how it will be. Okay, and now here, if you see, these are the variables or hyperparameters. Input size is 2, hidden size is 16. So it will be 2 cross 16 here and 16 cross 2 here. Okay, and the learning rate is 0.01. I want to train it for 100 epochs, and the batch size is 32, it seems. Okay, so for every 32 samples being processed for one step, 32 samples will be processed, and at that time, one backpropagation will happen. Okay, so that is mini batch SGD. Okay, so generate data, you will generate the data, you will split it as train test with the help of train test split. You are creating it as a torch data set, then making a data loader out of it, and then you are creating the model. The loss function is cross-entropy loss because it is a classification problem. When to use which loss when to use which loss, we'll see that later, because for each of those components already I have a dedicated section: activation function, loss function, optimizer, gradient descent. For each of those I have a separate sections for us to discuss with. Okay, let's not consider that right now. You have your cross-entropy loss right now, which is criterion. Your optimizer is Adam optimizer, where you'll provide the model parameters for it to optimize along with the learning rate. Okay, model parameters will provide the weights and biases for the optimizer to optimize with. Okay, so in the training loop, for epoch and range of epochs, so for every epoch, we'll set the model to train. At that time, let's initialize with the loss being 0, and we'll go through the training data loader to get the X and Y value. We'll send the X batch. So what the data loader will do is, it will create the X batch and Y batch with 32 values in it. Okay, 32 X values are sent to the model, which will provide 32 outputs, and that will be computed as loss with 32 true outputs. Okay, now you have your loss. Make sure that the optimizer doesn't have any gradients in it, because if it has, the updation will be wrong. So first set it to 0 gradient, start the backward propagation to calculate the gradients of loss, and then call the optimizer.step function to update the weights of model, like weights and biases, basically model parameters. Now we are just adding this loss so that we can print it. And this is how the inference code is. Okay, here if we run this, so it is taking some time. Now you can see it started and the loss ended up at 0.68, and apparently the accuracy is 52. It doesn't matter. Like, this is just for me to show you how it works, because this is very random data, so we can't expect any performance out of it. Okay, so yeah, that is how a simple ANN works. Now, what are the components we spoke about? Like, weights and biases are there. That's something we already spoke about. There is activation function, which will be the first thing in forward propagation, and then you have your loss function, which will be calculated, and then backward propagation happens, and then you have your optimizers, in which gradient descent itself is an optimizer. Okay, so for each of those components, we are going to see what are each of those, why should we use those, how should we use those, and types of each of this component. And for those as well, we'll see in detail explanation. So let's start with the activation function. Activation function are mathematical equation which will determine the output of a neural network. Key thing, highlight this. It will determine the output of the neural network, because that is what is the key for calculating and capturing the nonlinearity in the data. So they are applied to the weighted sum of the inputs at each neuron. I told you, right? Calculate the weighted sum and then apply the activation function on it to get the output. So that is what happens here in activation function. Why you should use activation function? It will introduce nonlinearity, like I said. It will normalize the output, keeping it in a specific range. For example, with ReLU, it is 0 to any positive number, because we don't want any negative number. That is the idea of ReLU. But there is options like Sigmoid, which is 0 to 1, or Tanh, which is minus 1 to 1. Okay, that will normalize the output, and it will enable the back propagation as well, because many activation functions are differentiable. That will allow the gradients to flow backward through the network. Okay, any function which is differentiable alone will allow back propagation, and activation functions are differentiable. How these would work? They'll take the weighted sum of the input neuron and apply a mathematical operation based on what activation function it is, and it will produce an output. This output becomes the input for the next layer, or final output will be out of the network. That also will be coming out of activation function. Now let's come to the type of activation function. First, most common activation function, which is sigmoid activation function. A sigmoid activation function is a S-shaped curve that maps any input values to a value between 0 and 1. Let me show you the curve for each of these type of activation function. Now, this is how the curve of sigmoid will look like. Okay, it is an S-shaped curve which will map any input values to a value between 0 to 1. Okay, and how it will map that? It is by using this formula, which is f of x is equal to 1 by 1 plus exponential of minus x, which is e power minus x. Okay, why you should use sigmoid activation function? It is useful for the models when you need to predict the probability of an output. As soon as I say probability of an output, you might ring it as, like classification maybe. Yes, if you have thought it like that, then good enough. It is for classification, okay? But since it is 0 to 1, it is good only when it is binary classification, okay? It is historically popular, but less used in hidden layers because it can map only between 0 and 1. That is not a case which you will see with the help of, normal linear networks. But this network is used widely in a very advanced network, which is LSTM. Okay, there it serves a different purpose. We'll see that in our LSTM section. Okay, so there is another activation function which is Tanh, and the formula is exponential of x minus exponential of minus x by exponential of x plus exponential of minus x. Okay, or if you want to say it conventionally, it is e power x minus e power minus x by e power x plus e power minus x. This is how the formula of tangent, hyperbolic tangent or Tanh is. And here, why you should use that? See, this is not a zero-centered curve. Okay, it is 0.5. It is not a zero-centered curve, but it is 0-centered curve here. So the derivative will be even better. Okay, and it will often perform better than sigmoid in hidden layers because it has a range of -1 to 1. More the range, better will be the value. Okay, with hidden layers. And this is how the curve is. As a comparison, the sigmoid will go like this, 0 to 1, but Tanh will go like this, -1 to 1. Okay, and you will initialize it like this. Okay, so if I call it here, my activation input will be 0 and 1 now. And then I'll be converting it to float, and here output will be 0.5 and 0.7311. How this output was calculated? It is by following this thing. Okay, this calculation 1 by 1 plus e power 0, 1 by 1 plus e power minus 1. Okay, something like that it will happen, and then it will provide you the sigmoid output. So similarly, we can do it for Tanh as well. So we will call the tangent hyperbolic tangent activation function, and then if you print the output, it is 0.000 and then 0.7616. Okay, so that is how it happens with hyperbolic tangent. But with linear unit, which is rectified linear unit, that is what is ReLU, it returns 0 for negative values and input value will be positive for positive values. Now, why you should use this? You see, exponential is a component which is very computationally intensive. Okay, that was the case with sigmoid and hyperbolic tangent, or Tanh in short. But rectified linear unit is a formula which uses max of 0, x. Like max value between two values calculating is very efficient. Okay, so that is one thing. And then if you continuously differentiate a value between 0 to 1 or -1 to 1, there is a very high chance that it will go to 0. Okay. In backpropagation, I said, right, you'll propagate the gradient and then you'll do differentiation. If you see, our weights reduced, right? The gradient value is reduced. At some point of time of continuous reduction, it will go to 0. Okay, that is vanishing gradient. Okay, at that time, your model will stop learning. And then this also induces sparsity in the hidden unit because, like the values are like that, basically. How? There is a sigmoid curve here. If you see, it is 0 to 1. But with ReLU, it is 0 to n. Okay, it is infinity. So if I do this, it will be 0.0 and 1.0. So you can see 0.0 and 1.0, right? But there was a problem with ReLU. ReLU had a problem of having 0 for negative values, and that created an issue known as dead neuron. Okay, to solve that, they attempted new method which is leaky ReLU. Okay, dying ReLU is what they said it as, or else that specific issue was known as dead neuron. Okay, where the neuron, once it gets stuck, right? Like once it goes to negative, it is not going to be become like, positive, because we'll always multiply it and it will become 0. After that, there will be no training. Okay. So what we'll do is we'll multiply it with a small, very small value for negative input. The formula will be that, it is x if x is greater than 0, and if x is less than or equal to 0, you'll multiply it with an alpha value which is 0.01. Okay, it will be like this. The leaky ReLU curve will be like this, where ReLU was like this. Okay, so if I give this here output, it will be the same as before, but to compare, what we are going to do is output, let's put it as ReLU out equal to ReLU of -1. Sorry, torch.tensor of -1. Torch.tensor of -1. Then we'll see that. Okay. So you can see it is 0. Okay. But if I do leaky ReLU of torch.tensor of -1, it will be something like -0.01. Yeah, it isn't implemented. All I need to do is -1. Now you can see here, it is -0.01, right? It is giving some value, which is very less, right? 0.01 is very less, but like it will make sure that the training continues. That is what is the advantage with leaky ReLU. If you think that, there might be a possibility for having a negative value, go for leaky ReLU. Now, softmax, a very important activation function, which you will use it very widely, even in transformers. So what it does is it will convert a vector of real numbers to a probability distribution. Okay. So it is used in output layer of multi-class classification problem. And then it will ensure that all the output values are between 0 to 1. E power x by summation of e power x, till j. So this curve will also be like sigmoid, okay, since it is 0 to 1. And what it will do is basically, if I print the output here, you'll understand. See here, the probability value of 0 is 0.2689 and 1 is 0.7311. Okay, that is what it is trying to say. The calculation is happening like this. Okay, basically what it is, let's say I have a multi-class classification problem of 10 classes. Okay, so what it will do is the network will say like, these are the values, or like, logits. That's what we say for each class. Now you need to convert it to a probability between 0 to 1. And for that, it will be applied with softmax. So basically, if you see, it is 0 plus 1 divided by value. Okay, that is what happens. Okay, that is what happens here. Number by summation of all the numbers. Number by summation of all the numbers. That is what happens here. Okay, so if I print the activation input, we'll be seeing, right? Okay, I hope you get that. So e power 0 by summation of e power 1. So summation will be like, let's do that. E is by E1. This is how it would be. Okay, because it is e power 0 plus 1. Okay, I hope you get that. So this is how the calculation will happen. If it was, let's say 1 and 2, it would have become E1 by E3 and then E2 by E3. This is how the calculation will happen. Okay, now like I said, the gradient will flow through this activation function, so you will differentiate it. Okay, so this is how the calculation will happen for most of the activation function, which is there already here. So here you can see there is binary step, logistic. Logistic is nothing but your sigmoid. Okay, there is tanh, arctan, ReLU, PReLU, eReLU, soft plus, like everything is there along with the derivatives. So if you plot the curve of derivatives, this is how it would be. Okay, tanh will be 0 to 1 range, sigmoid will be 0 to 0.25, and like sigmoid of 2.5, that will be like a sharper curve. And then tanh, like I said, it is 0 to 1. ReLU will be like 0 maximum, like, it will go on. It is not just 1, it will go on. Like, 0 or 1. There is nothing in between, either 0 or 1, because any number differentiated, it will become 1. Okay. That is what is differentiation, right? And then there is soft plus and Gaussian activation function, which will be like, derivatives curves will be like this, 1 and then like this. Okay. So when you should choose which activation function? For hidden layers, ReLU will be a default option, or else, like, if you feel, like I said, there might be a negative value in there, choose leaky ReLU. For binary classification, Sigmoid. For multi-class classification, softmax. For regression you can use linear activation, or you can use ReLU as well. Because ReLU, if you see, it is a kind of linear activation function if the value is above 0, because it will just provide the same value. Okay. So now we are done with the activation functions. All right. Let's move on to the loss functions. What are the loss functions? Loss functions are the measure which will be calculated by the difference between predicted output and the actual target. This will quantify the model's performance. If you are this much deviated from, like your target, then you have some issues, right? That is your error. So that is what is loss function all about. Why you need to use loss function? This will become a guide for you in the learning process by providing a scalar value, like, a quantified value that will show that, like, you need to be minimizing this value during training. And how these loss function work is that they will compute a score based on the mathematical formula it has by mapping the model prediction and true value as the values variables, like, to that variables they will map this, and that score will be used to update the model's parameters. So let's see about the types. First thing is mean squared error. A loss function that measures the average squared difference between predicted and actual values. This is usually good with regression problems. And when, like, why this is a very good error is it will penalize the large error more heavily since you are squaring it, right? The large errors will be more heavily penalized, so that it will know, like, yes, I have long distance to go. I need to, like, optimize myself faster, like that. And it is differentiable, making it suitable for gradient-based optimization. Every loss function will be mostly differentiable. Okay, how this will be calculating? First, you'll calculate the difference between predicted and actual value. You'll square those, and then you'll take the mean. Okay, if, for example, here there is 3, right? You will first calculate the difference between these. So it will be 1, and then what you will do is you'll calculate the square, which is 1 again, and then it will be 1 by 3. Okay, so it will be 0.33, something like that. Let's try. And if I print this loss, it should come as 0.33 if I'm not wrong. Yeah, here you can see it is 0.33. Okay, that is how mean squared error works. Cross-entropy loss. This is a loss which is very important because in transformers, everything is a classification behind. Okay, so you'll use cross-entropy loss and softmax activation function. Those two are very important as far as LLMs and transformers is concerned. So please, have a better concentration in these two components. A loss function that measures the performance of a classification model whose output probability is 0 between 0 and 1. Why you should use it? It is very suitable for multi-class classification problem, and it will work very well with softmax activation in the output layer. How you will use that? First, you need to apply softmax to the model's raw output so that you'll get the probabilities between 0 and 1. You'll take the negative log likelihood of the predicted probability to the correct class, and then you'll average that across the sample. That is how cross-entropy loss function works behind. Okay, so right now what I'm doing is, instead of, like, having it as 0 here, it was 0, 1, and then 0, right? So instead of 0, I just change it to 0.7. Okay, so if you see the loss now, it will be 0.7461. Okay, so if it was 0 itself, it is 0.55. Okay, so that is cross entropy. And binary cross entropy, it is a special kind of cross entropy where it is for binary classification problem. Okay, so since it is binary classification problem, Sigmoid activation function will be very good at the output layer. And how it works, it will be the same as cross-entropy. Instead of softmax, apply sigmoid, calculate the negative likelihood, and then you'll have your loss. So you can see it is 0.5665. Okay. If you see here, these two are very close, right? 0.55145665, because for both of these values, now I provided, a binary classification kind of an output, zeros and ones. Okay. That is how the optimization, loss functions are. Now let's move on with the optimizers. What are optimizers? Optimizers are algorithms which are used to adjust the network's parameters. If I say network's parameters, it is about weights and biases to minimize the loss function. Why you should use optimizers? It will implement different strategies to update weights, which can lead to faster convergence or better generalization, so that the model will update itself to wide range of scenarios. How do optimizers works? Once you compute the gradients with respect to loss, this will update the parameters, and with respect to the parameters, it will update them accordingly. Like I said, when you call the loss.backward, all those gradients will be calculated, and the updation will be done with the help of optimizers only. Okay. The optimizer types of stochastic gradient, ADAM, and RMS prop. These are the three main types of optimizer. There are other types like ADAM with weight decay, ADA, grad, and so on and so forth. But we are gonna focus on these three alone. Okay. Stochastic gradient descent is one of the most basic form of gradient descent, which will update the parameters based on a gradient of the current mini batch. What is the mini batch? For example, I had a sample of 1000 here, right? I had 1000 samples here, in which we took 32 as a mini batch for one step. We'll update the value only for based on those 32, right? So that is what is optimizer, which is SDD optimizer, like mini batch SDD. That's what they call it. Why you should use that? It is simple and memory efficient. It can escape the shallow minima due to its stochastic nature. So basically, gradient descent will go like this, right? 1, 2, 3, 3, 3, something like that. But stochastic gradient moves like this. If it is a circle like this, it will move like this. Okay. So it can escape the local minima a bit. So how this will work? You'll compute the gradient, and you'll update each parameter by subtracting the linear learning rate multiplied by the gradient. Okay, that is what happens with SGD optimizer. And if you print that, these parameters will be shown. Okay, the learning rate is 0.01, and then there is momentum as well. Okay, in SGD there is momentum as well, but if you want, you can provide that, or else you can just leave it. Okay, we didn't provide weight decay as well. So this is the most basic form of optimizer, and this is a revolutionary optimizer. This is the optimizer which is used even nowadays, but it was found long back. It is an adaptive learning rate optimization algorithm that computes the individual learning rates for different parameters. So what it will do is, initially it starts with the learning rate, and then it will update the learning rate also. Okay, so here it will combine the benefits of two optimizer, which is AdaGrad and RMS prop. RMS prop, we'll see about that here. And there is issue with AdaGrad, which is diminishing learning rate. That was solved by RMS prop, but there were some other benefits with AdaGrad, which also was included with ADAM. Okay, this will work very well with data where there is no noise or sparse gradients. So basically, ADAM can be used anywhere. How it works, it will be maintaining a moving average over the gradient and the squared gradient, and those will be used to compute the adaptive learning rates for each parameter. Okay, so that is what ADAM optimizer. And RMS prop is an optimizer that adapts the learning rate again based on the gradient history like ADAM, but what it will do is this will just maintain a moving average for the squared gradient, and then it will divide the learning rate by the square root of this average. That's all. Okay. So that is how RMS prop works. We don't want to go into details a lot of optimizer. That is why I'm just simply saying this is how it works. Finally, we have gradient descent. That is an optimizer by itself, but gradient descent is something we need to spend some time on. So that is why I said it. It provides a way to find the optimal parameters that minimize the solution. How it will do that? We know, right? we know right now about that. We'll compute the gradient of the loss with respect to each parameter, and then we'll update those in the opposite direction. The types are batch gradient descent, which will be doing it for the entire data set. Mini batch gradient descent is doing it for small batch, which we saw. Okay, stochastic gradient descent will do it for single sample. This is the difference between each. Mini batch SGD, what it will do is it will do the stochastic gradient descent on a mini batch which we provided. Okay, otherwise the formula is the same for each and one of these. Okay, so now you have a initial idea about ANN, all the components which are involved in a neural network training. In the next part, we are going to see about RNN networks, because these play a major role with natural language processing, because RNN were created for sequential data, and NLP is basically about sequential data. Okay, text is sequential, right? So in the next part, we are going to see about that. Hello everyone, welcome to the Intermediate Prerequisites Day 0 Part 2. So now we are going to see about the RNN networks in detail. In the RNN networks, there are 4 primary networks which we need to know about. One is the first RNN network which came into the picture, which is RNN by itself, and then others were modified out of it, which are LSTM, and then BiLSTM, and then GRU. All are RNN networks, and we are going to see about these networks in detail. Let's start with the recurrent neural network. So, what is recurrent neural network? Recurrent neural network is a class of artificial neural network. All were derived from ANNs only, which are designed to work with sequential data. Unlike feed-forward neural network, which is your ANN, RNN have connection that forms directed cycles, allowing them to maintain an internal state or memory from previous inputs. So what is this definition all about? Just forget these, alright? From x0 to xn, just consider that xn is your input and there is an ANN cell here, okay? And then there is dense and then output is obtained. This is how an ANN works. But with RNN, what they did was, if there is a sequence of data, let's say your batch has 5 inputs, okay? You have stock price prediction as your use case, and you have your close prices of past 5 days, and you want to predict the next days, okay? So first you will send the first day's price in x0 along with the date, and then you will send second day's price in x1, where the first day's price information is also provided to the second days. Okay, there will be a recurrence inside. Okay, and that is what is shown here. If you give a xi, the si, which is the state of RNN, will be recurrently provided to the RNN cell itself, and the final output will be obtained with the help of dense network. So I hope you are able to understand. Okay. In case of ANNs, there will be only dense network. Okay, there is no recurrence inside that. And since there is a recurrence of state going on behind, that is why it is called as a recurrent neural network. Right? Now, it begs the question, how and why the model was created. Yes, there were good models like ANN and CNN, but why RNN came into the picture? So RNNs were developed in the 1980s to address the limitation of traditional neural networks in processing sequential data. If you are processing a sequential data, it is very important that you remember the past, which is your sequence. That is not something all the previous models, which were like ANN, CNN, your machine learning models, any of those models couldn't remember the sequence. So they thought, okay, let's create a network which will do that. So for that, the motivation was to create a network that could use its internal memory to process a sequence of inputs, which will be making them suitable for tasks like speech recognition, language modeling, and so on and so forth, wherever there is a sequence of data involved. So basically, NLP, if you see, is all about a sequence. I'm talking now, and I'm talking in a sequence, right? There is a word after a word. Or if we see as the model, there is a token after token, right? So the key motivation was to create a network that could use the model's internal memory itself to process those sequence of inputs, which makes them suitable for tasks which involves NLP and also time series. Because time series is also recurrence, right? Now let's see how the model works. All right. What is the basic structure? An RNN consists of input, hidden, and output layers. That is very usual. The hidden layer has a self-loop connection which allows it to pass information to from one step to the next step. Like I said, x0 is one time step, x1 is the next time step, and x0 output state is provided to x1. Similarly, it is provided till xn, right? There is a recurrence. So that is what is said as loop here, self-loop connection. So forward pass, how it happens? Let's say there is a time step t. The RNN will take an input xt and there will be a previous hidden state. Hidden state, let's call it as h, okay? And since it is previous hidden state, we'll call it as t minus 1. So ht minus 1. So to compute the current hidden state, why we are calling it as current hidden state rather than output is because here we'll compute for RNN cell, not the dense network. Once it passes through the dense network, that is when we'll get the output. Usually dense networks are very good with one thing, which is to aggregate the information or expand an information which is already there. Okay. So right now we are looking to extract the information across temporal division, okay, which is time. That is why we are calling it as hidden states, okay, rather than outputs being passed. So to compute the current hidden state, the formula will go like this. If your current hidden state is ht will be calculated by tan h, which is an activation function, will be equal to, ht is equal to tan h of weight of hx, okay, into xt, which is just your wx transpose plus b. That's what we do, right? So that is what is here. But what we'll also do is we'll also provide the weight of hidden state of previous time step. That is why it is whh star h of t minus 1. Okay, so that is why we'll do. That is how we'll do. Every state will be calculated by adding up the information which was there in the previous state. Now you might wonder, what happens if I move 10 states before? You see, there is an advantage and disadvantage in there. The advantage is that you will reduce the computation and it would not be required as much because that previous state would have the information of all those previous states and so on and so forth. There is a sequence, right? But it is also very important that the first information comes to the last as well, because every hidden state processes it in a different way, right? That is a problem in recurrence. It will happen with the previous time step alone. Okay. So here, if you see hx and hh are weight matrices, as you all might know now, and bh is bias. So this is nothing but tan h of w transpose x plus b. Okay. And w transpose x plus b is the common function for any neural network to work with. Okay, but here what we are doing is we are adding the previous time step values also, that is by whh star h of t minus 1, right? So that is how the forward pass will happen. And if you know the forward pass, that's how the model works indefinitely, right? It will go on and on. So how the output computation will happen? If you are doing inference or final output, something like that, the output yt is computed based on the current hidden state. Like I said, you will compute the hidden states till that timestamp, and the output will be computed as why. Y is a weight matrix of your output into h of t plus b of y. Okay, this is as similar as this, but here the hidden state of current time step, which is calculated here, is provided here. That's all. And where this output computation will happen is, it will happen in dense network. Okay, that is why I said we are calculating the RNN cell forward pass here, and the output computation will happen in the dense cell. Okay, So that is your output computation. And then how the backpropagation will happen? The backpropagation will happen through time. Okay. RNNs are trained using BPTT, which is backpropagation through time network, where what it will do is it will unroll the network through time and then it will apply the backpropagation. Because if you see, we are going everywhere, like, one state before, right? Hidden state before. So it will also do the backpropagation like that, one state before. In everywhere, like, for the previous state also, backpropagation will happen, tracking back to the 0th cell of 0th state. Okay. That is how the backpropagation through time will happen. And what happens is, after each time step, once you compute the gradients, it will be summed up together. Okay. So that is how the backpropagation through time happens. And then you have your gradient flow. How the gradient flows? During training, the gradients can vanish or explode as they are propagated back through time, making it difficult to learn long-term dependencies. Like I said, it will flow through time, and since it is flowing through time, if you know backpropagation is kind of using differentiation. Okay, and with differentiation, always the value will become lesser. So at some point of time, there is a chance that it will either vanish, or if it has some weird weights, exploding is not something which will happen commonly. But if there is some weird weight initialization, there is a possibility to explode the gradient as well. Okay. So if you see as an example for RNN in a character level language model, which is to predict the next character, each input XT is a character. Like I said, one character will be XT and the network will predict the next character, which is YT. And the hidden state HT captures the context of previous characters. For example, if I say example, right? Let's say our current hidden state is, or like our current sequence timestamp is M. Okay. So EXA, all will be there in the hidden state. M will be my XT, which is the current character. And the idea is to generate P, which is the next character. Okay. That is how RNN basically works. If you are using a character level RNN, when can you use RNNs? RNNs can be generally used when you have use cases like time series prediction, natural language processing tasks, whatever it is. Okay. Again, these are the state of the art models then. So if we are seeing it now, yes, we'll feel like, okay, this is boring. Like, the performance is not that good. But imagine that these happened in 1980s, right? At that time, these kind of models are pretty huge. These were revolutionary models then, right? So those were used for natural language processing tasks then, and it can be used for speech recognition, music generation, because all of these are working on a temporal dimension. Now let's come to the advantages and disadvantages of this model, because to know the limits of the model, it is very important, right? Or else you can't use it for your real use cases. So it is very important to know the advantages and disadvantages. So what is the advantages of RNN? It can process sequence of variable length. Like I said, all it cares about is a sequence, and the previous time step value will be provided to the current time step. That's all, right? So it can process sequences of variable length. It will share parameters across time steps, which means it will reduce the number of parameters to learn. Okay. And then we have the capability to capture temporal dependencies in data. Temporal is nothing but time, right? So these are all something we know. So what are the disadvantages? First, like I said, since you are doing backpropagation through time, there is a problem of vanishing or exploding gradient problems which might occur. And then there is difficulty in capturing long-term dependencies, because let's take ourselves as an example, and then we'll be able to understand what happens with RNN. Okay. RNN expects on the fact that you should remember all the things which happens previously. Let's say I put you to the task of remembering what all you learned from your first grade till 12th grade. Okay. You need to remember each and everything. Would you be able to remember that? I can't remember. Maybe you can. But still, it is very difficult, right? So that is why it is very difficult to capture the long-term dependencies. It is computationally expensive, long sequences, right? Because you are calculating each and every time step, right? If I go for 1,000 token sequence, you will remember all the hidden states of all the 1,000 tokens when you are coming to the 1,000th token. Okay, so it is very computationally expensive because it is very additive in nature, in sequential rather than parallel. Okay, why I am stressing on that, you will understand when we go to the next section. Okay, now let's see about another model which was more revolutionized in any field which involved time over RNN, which is LSTM. So LSTM network is a network which revolutionized a lot of things which when it came, because it applied a special form of RNN to capture the long-term dependencies. You see, if we want to remember the old things, we'll try to forget not important things, and then we'll remember those things which are very important for us alone, right? So that is what even LSTM does. It will selectively forget and remember informations over time. Okay, let me first show you the image in detail. So yeah, it is a bit blurry because I have scaled it, but yeah, I hope I'll be able to explain it correctly. Okay, so here, this is how the RNN network is. All right, and here if you see, here you have an X here, right? This specific place is your forget gate. Okay, and here this specific place is your memory gate, and this is your output gate. So it has three gating mechanisms. And why is that? Why is this forget gate, why is this memory gate, and why is this output gate? We'll see about that. Okay, that is for detailed working explanation, but this is how the architecture is. Okay, so let's start with how and why the models were created. So LSTM, if you see, was introduced to address the vanishing gradient problem, like I said, which was there in the traditional RNN, because over time the gradients will be vanished because you will differentiate the gradients at every step. The goal was to create a model that could learn and remember information over sequences, which is crucial for any real world applications which is using time steps, right? So basically how the model works, let's see that. Okay, an LSTM cell will consist of a cell state and three gates. Okay, so what is the cell state? This is your cell state C. Okay, the C is your cell state, and in the cell state, along with that, you have three gates, like I said, which is forget gate, input gate, and output gate. Forget gate, what happens in there? Sigmoid of weight of F timestamp, wait, just forget F. Okay, weight star previous hidden state, comma, current state. Okay, current value. So this is nothing but the similar thing which happened in RNN. Okay, you will multiply these and then finally you will add the bias. Okay, but what here happens is we'll make a sigmoid. Okay, so before going through that explanation, let me show you what happens here. Okay, let's say a variable is coming up here, or the current time step. Okay, and here there will be some previous time step informations. Okay, and this is your memory channel or cell state. Here what happens is, once a current value appears, let's say there is about 10 time steps which is stored in this hidden state information, which is also there in the cell state. That is fine. Here what we'll do is, in that 10 state, we'll add the 11th state, which is the current time step, and then we'll multiply with W transpose X plus B in that format, and then we'll apply a sigmoid function. If you see the sigmoid function, its differentiation range, activation function range is 0 to 1. Okay, so if the value is 0 to 1, what happens is we'll round it. Okay, 0 or 1. If you want to forget it, this information will be forgotten because here there is a multiplication. It will not be added to the memory channel, which is the cell state. I hope you get that. There is a cell state, and you're multiplying the current values here. Okay, so we are just basically multiplying, and we are saying like, okay, see, I want to forget it or I want to remember it. Okay, that happens in here. So I've forgotten things which I need to forget. Sorry. Now what I'll do is how much I need to remember. You see, again, if I need to remember or not, that will happen in the sigmoid function. But how much should I remember? That is something we need to check, right? Because how much should I give importance and remember is something even we do, right? Like if we say like there is a very important question, we'll read it again and again for 5 times, so that we'll remember that for a longer time. So that intensity is provided by the Tanh layer. Okay, so what happens here is the sigmoid will say like, how should you remember or not. That is like as same as the forget gate. But when you do the same process, rather than applying sigmoid, you'll apply Tanh. The Tanh range, activation function range, is -1 to 1. And here, so if it is -1 to 1, you will know, like, the intensity. Should I remember it negatively or should I remember it positively? If so, how long should I remember it or how much I should remember it? If it is close to -1, I need to negatively remember it, right? Like, this is something which is an anomaly. Okay, so let's say there is stock price, there is some price going down, I need to negatively remember it. Okay, I should not sell here, I need to buy here, something like that. Okay, and if it is going upwards, I need to remember it positively, something like that. Okay, that is what happens with Tanh. So these values will be multiplied. So if I want to remember information, it will say 1, and how much should I remember? It will be set by Tanh, and those will be multiplied and then will be added to the cell state. Okay, that is what happens in the memory. Okay, in output gate, what we'll do is we'll again see if this is something which is constituent to provide output, that is by sigmoid, and then the value which is there in the cell state, because that is what is your, let's say, your brain memory. Okay, this is your brain memory. You have all the informations of your previous occurrences. Let's say what you'll do is, again, you'll apply the Tanh activation function, and then with this just Tanh activation function, this is W transpose X plus B, on top of which Tanh is applied. That's why it is in a box and that is orange. Okay, that is a layer, but this is just Tanh activation function. Basically, whatever value is there in this cell state, it will be computed with Tanh, and those values will be multiplied. Okay, and finally, whatever you need to remember and how much you need to remember, those will be remembered, and that will be applied to this output, and your hidden state is obtained. This is how LSTM works. I know this is complex, but like, just remember that you are learning. If you want to forget, you'll forget it, right? You'll just ignore those. You are filtering it, right? Like, I'm not even gonna read this. So that is your forget gate. So if you want to remember it, let's say you'll have negative memory and positive memory, right? The tough questions you found it hard to remember, you will remember it negatively. Okay, I was struggling hard to learn this question. So that kind of memory is provided by memory gate, which you'll add to your brain. And finally, based on those knowledge, you'll try to answer a question which is provided at timestamp t, right? So that is how it works in real time, right? So those knowledge, you are trying to use it, and you are providing the current output. Okay, so that is how LSTM works. LSTM was actually designed based on brain. Okay, brain, how it works. On that inspiration, LSTM was designed. If you see here, actually, I didn't even spend this much time on RNN. LSTM is very important. Okay, so more than RNN, LSTMs were used a lot of times in those times. Okay, and even till transformers came, LSTM were used till, let's say, 2018. Because 2017 attention is all you need paper came, but it didn't pick up soon. Okay, so once the pre-trained models came, that is when transformers took over the market. So until then, LSTMs were the go-to model for any person who is working with NLP or time series. So here, like I said, the forget gate is to you need to forget it. Input gate is nothing but your memory gate. Okay. And this will decide what new information you want to store in the cell state. And then there is cell state update. Okay. Like I said, there is star and then there is your plus and all, right? And those updation are cell state update. And your output gate, like I said, it is to apply the Tanh along with Sigmoid, sorry. Here you can see Sigmoid layer is applied for timestamp t, and then those values, which is O of t, is multiplied with the Tanh on whatever cell state we have currently. So this gate will control what information from the cell state is required for output. Okay, so that is your output gate. So example, in a sentiment analysis task, the LSTM can learn to focus on key words or phrases that indicate strong sentiment while forgetting less relevant information. So this is a very good example. Let's say I'm saying the movie was very good. I liked it so good that I watched it second time. Okay, I liked it so much. Okay, let's put it that way. If it was RNN, it will give equal value to all of those words. Okay, but with LSTM, what it will do is it will focus on these words like very good, like, so much, which means it is a positive sentiment, right? That is how even humans do, right? We'll not focus on all those words. We'll focus on few words, and LSTM does that. Okay, so when you'll use this, which is like it is as similar as RNNs, like where RNN use cases, wherever RNNs can be used, LSTM can be used as well. So advantages is that it will capture long-term dependencies. It can mitigate the vanishing gradient problem. It has selective memory like in humans through gating mechanisms. It will have robust performance across wide range of sequence lengths. Disadvantage is that it is more complicated than RNNs, and so it will require computational resources. Okay, and then it is very challenging to train. So like, if you don't initialize it correctly, it will not remember it and it will not correctly forget things. So it is very challenging to find the hyperparameters which are correct to train. And then it has potential for overfitting, especially in smaller data sets, because it is very good model. It doesn't have a lot of normalization in it. Okay, so that is about LSTM. So before going into the next model, I would like to ask you all to hit the like button, share it with your friends. If you haven't subscribed to this channel, please hit the subscribe button, hit the bell icon so that you won't miss any day video which I'm uploading right now. And also, these are just free for you, but it means the world for me because the algorithm works only based on your likes and comments and your shares. Okay, so please help me with that and help me reach 10k subs. With that being said, let's go to the next model, bidirectional LSTM. Bidirectional LSTM is an extension of standard LSTM that processes the input sequences in both forward and backward direction. This allows the network to capture both past and future states, which will provide more comprehensive understanding on the sequence. So if you see in LSTM, we remember the past, right? The past sequence. But let's take time series analysis out of the equation and let's put something like sentiment analysis. Okay, let's say I have a sequence like this. The movie was very good, but I didn't like it much. Okay, here the it refers to the movie. Okay, let's take another example. I didn't like it much. Okay, this is something not grammatically correct, but let's take this as example. I didn't like it much, but the movie was very good. Okay, if I'm doing it in the opposite, here the it constitutes the movie. Okay, but if you don't know what happened in the future, you won't be able to know, it refers to the movie, and the movie was very good, so it will say positive, but it is negative, right? Because I didn't like it. So it is very important that you remember the future states as well. So that is why BiLSTM happens. Okay, so for BiLSTM, what happens is each state which we get will be sent to the next state, which happens in the forward LSTM, and in the backward LSTM, what it happens is, so those information, let's say there is your first, second, third, and fourth cell, and here the information is in forward, and backward LSTM will be in backward. So here it will be 0, here it will be 0. So 0, 1, 2, 3, 3 to 4, and 1 to 2. So the 1 to 2 information is crossed between 3 to 4. So the information is shared. Okay. So that is what they are trying to say in forward and backward LSTM. Okay. So why this model was created? Like I said, there are tasks in NLP which required understanding of the full context of sequence. Basically, NLP requires full context sequence understanding. Okay, anywhere it is, doesn't matter. So what is the working of BiLSTM? So BiLSTM consists of two separate LSTM layers. One will process the sequence left to right, another one left to right to left, like we said. So forward LSTM, what it will do is it will be working on forward. Again, it will be based on the timestamp t minus 1. But since backward LSTM happens from right to left, it will be working on with t plus 1. Okay, so that is what LSTM forward and backward is. The output will be concatenation of the information which is obtained from the LSTM forward and LSTM backward, and based on that you will get the hidden state, right? So those hidden state again will be multiplied with the dense layer, which is going to be wy star ht plus by, which will be the weight matrix and bias vector multiplying to provide your current output at timestamp t. So while training, backpropagation will happen through time, as like in LSTMs and RNN, but will happen simultaneously for both. Okay, so it will be right to left for forward LSTM and left to right for backward LSTM. The backpropagation will happen like that. Okay, so the use cases, again, any NLP use cases can be said as a use case for BiLSTM, because it captures past and future context. It improves the performance in tasks where there is importance for bidirectional context. It reduces the ambiguity in classification tasks, and also it can be combined with attention mechanisms for even better performance. Okay, so that is a hint, as you all might know, of what might be coming up in the next video or next videos. So the disadvantage is that it is even more complex than unidirectional LSTM, because you are just replicating that again and then you are processing it in the opposite direction. Already LSTMs are very computationally intensive, and just think if you are doing it twice. Okay, and this requires the entire sequence to be available before processing. So like that makes it a bit unsuitable for real-time applications. If it is not real-time, let's say it is sentiment analysis or generation of something, like that is not real-time. What is real time is, for example, you want to real time you want to recognize what you are speaking, speech recognition. That is not something which you can do with the help of BiLSTM. So now already LSTMs have the potential for overfitting, and you are literally making another LSTM on top of that, which makes it more potential to overfitting, and then it is more complex to implement and fine tune. Okay. Now let's see about the next network, which is gated recurrent unit. Now you might see, okay, this looks like LSTM, right? Yes. GRU is a type of recurrent neural network which was made as a simpler alternative to LSTM, because it uses a gating mechanism to control the information flow, like how it happens in LSTM, but this is more simplified. Okay. And why is that? Let's see. Okay. So let me say simply how it works. Okay, first just remember what I said in LSTM, right? There was a forget gate here, okay, which will forget whatever information which needs to be forgotten, and it will add it to the cell state, right? And how much it should remember will be obtained from here, and it is provided to the cell state, and then again you will have your output gate here. Okay, so that is how happens in LSTM, right? Here, the forget gate and output gate is a bit combined. Okay, so what happens is the hidden state is there, which is your cell state here. The cell state will provide the past information, and again, what you will do is you will see how much you need to forget here. That is what happens here, and that will be directly provided to your update gate. Here there is only two gate. One is reset gate, which is there here, and there is update gate. Why it is reset? Here you can see it is into, right? So if you see like, the current time step, it doesn't use a lot of information from the previous time step. That is what is obtained from here. It will say, okay, I need to forget it. It is combining the memory gate, output gate, not the forget and output. It combines the memory and output. Okay. So here you can see, it will say like, if you want to remember or not. If you don't want to remember, it will reset it. If you want to remember, it will not reset it. Okay, that is what happens here. And if you don't want to remember the past, okay, that information is already provided from here. Okay, this sigmoid, and how much you want to remember, that is obtained from this Tanh, like we see in the memory gate, and this will be something which we see in the output gate, and those are multiplied together and are added together in the cell state, which will be providing your output. If you see, functionally, this looks like LSTM, right? But there is one gate which is reduced, which is memory gate. Okay, the forget gate acts as the reset gate here, and there is output gate already. Okay, so that is your update gate. So basically, your memory gate is alone not there. Memory gate and output gate are combined together as update gate. That is how GRU works. Okay, so here there is a mathematical explanation, and you can see that as well. So this gate basically decides how much information of past is to pass along the future. That is what happens in update gate. And the reset gate will say like how much information I should forget. The candidate hidden state, which is nothing but C of t, okay, which is there here. So those will have the memory content, okay, like, which you need to update it to the hidden state. And the hidden state update is nothing but the plus. Okay, so basically in text classification or any use cases where LSTM can be used, you can use GRU, but make sure that the computational efficiency is the priority, not the performance, because this is not gonna be as good as LSTMs. Okay, it is not gonna be as good as LSTMs, but it is going to be very computationally effective than LSTM. That is what is the advantage. Simpler architecture than LSTM because it has fewer parameters. It is efficient at capturing medium to long range dependencies, not very long range. Faster to train and run than LSTM. Comparable performance to LSTM on many tasks. It is not better. Comparable, which means it is closer. Okay, so if you want performance, go for LSTM. If not, if you want computation efficiency, you can try GRU. Okay, it is less powerful than LSTM, so some complex task, it is not good. It is less studied and understood compared to LSTMs. LSTMs, like I said, is used widely even now. So, like language models are there. Even there are few people who try to use LSTMs nowadays. Performance, again, can vary based on specific task and dataset. And it can't do long-term dependency tasks as LSTM. Usually AI works very well when, the works are separated and provided. Here, like the memory and output gate are combined. So two works are done by one gate. So it is, expected to not work very well as much as LSTM. So now we have an idea about the most famous kind of networks in RNN. There are networks like Peephole and all, which came and went. Okay, but these four are the most primary networks which are used in RNN, and we have seen about these four in a brief manner. Okay, now you have an idea basically how this model works. Maybe you can work on these things and then explore on your own way for these, but these kind of information is more than enough because our focus is to learn more about the language models, right? So these information are required because that is when you will understand why language model came into the picture and why it is still good, okay, and are having more advantages over these kind of networks. So now that we have a theoretical idea about the RNNs, let's try to build a story writer with the help of RNN networks here. Okay, so don't fear that there is around 500 lines of code here. Okay, so these are just having lot of doc strings, and I have made it in that way because like if you're gonna refer the code once again and again, you can't watch this video again and again, right? So that's why the code is made in such a way that you do not need to watch the video again and again. Okay, so I'll explain the code now, and then we'll see how we can train, because here we'll see how we can write a torch dataset, how we'll write a data loader, everything will be covered. So let's jump into the code. Here you can see we have some few imports. We have torch, which is the deep learning library, the most famous deep learning library nowadays, which is used to create neural networks and so on and so forth, any kind of neural networks. And those neural networks are provided in this module NN, because torch is a parent library, and inside that there is a module which is for neural networks, and there is Optim, which is for optimizer. Optimizer is responsible for your backpropagation, learning rate updation and all. And then you have your data, torch.utils.data, in which you will have all the data utilities, in which we'll call the data loader and data set, which is used to provide the data to the model. Okay, so first we are writing a config class. So configuration class for the text generation model, which will hold the hyperparameters and configuration settings for the text generation model. So here there is embedding dimension, which is the dimension of word embeddings. If you remember the previous section, which was beginner prerequisites, in which we said we saw that word embeddings with increased dimension, it will have more better understanding about the relationship between words. So if you are remembering it as TF-IDF, it is the max features. How much features you are gonna represent a word. Okay, so that is your embedding dimension. So higher the dimension, better the performance, but it will require more computational resources. Hidden dimension is the dimension of the hidden state in RNN, LSTM, or GRU. Okay, and then you have your number of layers. How many layers do you want? So one layer will have the cell state, which we discussed in the theory. How many cell states like that you want to replicate? Again, everything, more the number, better the result, but increase in time, increase in size, increase in computation, that will be there. Sequence length, it is opposite here. Longer the sequence length, more memory, more difficult to train, but an appropriate training length is required. Batch size. In training, each batch, how much sequences you are expecting to provide. So that is batch size. And then you have your epochs, which is the number of epochs you want to train the model on. So how much time you want to train the model. It is how much time I'm writing and seeing myself, or reading and seeing myself. That is your batch epochs. And learning rate, at what rate I want to learn. That is your learning rate. So optimizer is what will make the model to learn. Okay, so you are setting at this rate learn. And UNK token is unknown token, so you will have a vocabulary of words, and if the word is not, or if the token is not there in the vocabulary, it will say unknown. Okay, so here the values are provided. Embedding dimension is 256, hidden dimension is 512, num layers is 4, sequence length is 10, and batch size is 32, epochs is 25, learning rate is 0.001, and UNK token is UNK. Okay, so in tokenized text, we'll tokenize the input text into words. It is to just split on space, and we'll convert the whole text to lower space, and then we'll lowercase, and then we'll split it. Okay, so here if you see, let's say this is the example, hello world, how are you? It will be split as hello world, everything is in small, how are you? Okay, so that is what happens with text.lower.split. Now we need to create a torch dataset. Okay, so here the torch dataset has two things. One is length and another one is get item. Now we are doing a character level data, so which means every character will be provided. So if the data has 100 tokens, the sequence length is 10, the length will return 90. Okay, so that will show how much number of sequences are there in the data set. So the get item, what it will do is, let's say there is data 1 2 3 4 5 and your sequence length is 3. what it will do is it will split it as 1, 2, 3 when you call 0, and it will do 3, 4, 5. Sorry, 2, 3, 4 if you call it as 1. And then, like, see, it is just how much timestamp you wanna cover. You wanna put that way, like, that will be better. So if I say timestamp 10, there will be let's say my timestamp is 2 here. Okay, so if I call 0, it will be 1, 2, 2, 3. Okay, if I call 1, it will be 2, 3, 3, 4. So that, like, that recurrence of remembrance is there, and that is how you provide it here. And that is why we are subtracting the sequence length from the length of data. Okay, this is how you will construct a torch dataset for RNNs and LSTM for a character level. Okay, or not just character level, any token level. Now let's create the model where we'll use these attributes or parameters, where we'll get the model type. So what kind of model we want? LSTM, RNN, GRU, BiLSTM. Okay, and then we have embeddings, and we'll provide the RNN modules as well, which will be there, and then feed forward. So these are there as attributes, and the arguments which we'll provide is vocab size. Like, what is the vocabulary size? That is what is going to determine your embedding, along with the embedding dimension. Like, what happens is, let's say my vocab size is 50 and my embedding dimension is 512. Each of those vocabulary tokens will be represented in 512 dimension vectors. That is what will happen in N100 embedding, and this embedding will learn itself and update those vectors. Okay, and the hidden dimension, like I said, like, what is the dimension of RNN and the number of layers and model type. So based on these, what we'll do is, if the vocab size and embedding dimension is provided, those will be instantiated with N1.embedding. And if the model type is RNN, we'll call RNN, LSTM, GRU, BiLSTM. What we'll do is bidirectional will be set to true. Okay, and if the bidirectional LSTM is set to true, the feed forward will become 2 times the hidden dimension and then vocab size. So feed forward is nothing but your dense. Okay, like I said, the dense is what will aggregate the information, right? So it will aggregate all those hidden states, and then it will multiply based on the vocab size to say, like, this is the next token. Okay, so if it is not BiLSTM and it is like, normal models, the hidden dimension will be the same one. Okay, so now the forward pass, what happens is, first you'll compute the embeddings, and that will be provided to your RNN. So that will provide your output and hidden state. Okay, so you will provide this output alone to the feed forward network, and then you'll get the output, but you will return the hidden state because that is what will be used in your backpropagation and all. Okay, so the initialization of hidden states. The hidden states, when you want to initialize it, you'll initialize it as, like, zeros. Okay, so you can initialize at zeros as like it is provided here. Okay, you want to get the model, like, these are auxiliary functions, helper functions. To get the model, we'll call the text generation model with those parameters, and lot of things are provided in config class, and some are provided as parameters which are used here. Okay, vocab size and model type is provided as parameters, those are used here, and others are provided as config from config. Okay, when you call the train model, what we'll do is, first we'll import the loss function. So for you all who don't know the loss function, what is loss function? Loss function is the one which will say, like, how much you are deviated to the current output. It is like the teacher putting you mark, but like, lesser the mark, better the performance. Let's say your teacher only puts negative marking. Okay, lesser the negative marking, better your performance. And based on those negative marking only, you will improve yourself, right? So that is your loss function. And the optimizer is Adam optimizer, which is the most famous optimizer. So before, like, going through these, I'll recommend you all to have an idea on ANN optimizers and loss functions and all. Okay, so the optimizer is obtained, and when you call the model.train function, what happens is, for epoch and range of epochs, like, number of epochs you want to train yourself, we'll go through each of those data, and then we'll initialize the model, and we'll get the hidden state, okay, of the model. Like, we are initializing it, right? Because you need something to start your time step. Okay, that is what is the initialization of hidden state. Because in case of RNN or LSTM or GRU, it is expected that you have a previous hidden state, and those previous hidden state at first time step is going to be 0. Okay, that is what we are doing here. Initially, the optimizer is set to 0 gradient, and that is provided to the model. Okay, the output or your your input and hidden are provided, and you get your output, which will become your input later, because that is what is there even in hidden state. Okay, and then you have your loss, which is calculated, and then you'll make your back propagation based on the loss, and then you'll call the optimizer that step function, and then here it is just logging the loss at time step. Okay, so this is your training function, and the inference function, which is to generate. First, we'll call the model.eval function to set it to eval mode, and then tokenize text, because once you get the text, you need to compute it as tokens, and you need to make the input tokens IDs, because there might be some tokens which will not be there in the vocabulary, and those you need to replace by UNK tokens. So that is what is happening here, and then you'll convert it as tensor, and you'll initialize the model hidden state, and you'll start your generation. This method is known as greedy decoding, where what we'll do is we'll call the model to generate the next token, and we'll see what is those token, and then we'll add it to the all the previous tokens. Okay, that is what happens here. The input sequence is there, and the next word IDX is there. Those will be added and then will be provided to the model again. This will be recurrent. Okay, the next best token will be calculated again. Okay, the next best token is obtained from here. So which will say across the 5,000 tokens, this is most likely to be the token. That is what is provided with this argmax, and that will provide your data text. Okay, so while you're creating your data set, first we are tokenizing the text. Okay, and once the tokenizing is completed, we are making a vocabulary based on calling the set. Set will basically remove your duplicates, and that will create your vocabulary. And then what we are doing is we are just providing index to word and word to index, so that you can map it forward and backward. And we are having a function to add UNK token. Okay, because it is not always possible that you will cover every tokens which you might see in the real world. For example, capital A and small a are different. Okay, so in those cases we need a UNK token. Those are added here. Finally, what we'll do is we'll convert those story which we tokenized as tensor. Okay, tokenized IDs. Okay, that is what will be there as data, and those will be provided to the story data set, and then DataLoader will combine this data set and make it as a batch, and then it will shuffle it and provide it to the model. Okay, that is what will happen with DataLoader. Then you'll call the train and save model, which will get the model, train the model, and save it. Okay, so this is basically the function which will integrate all of those other function. And then load model to load the model while you're inferencing it, because if there is a model which you trained already, you need not train it, right? So we'll load the model, which is text generation underscore, for example, if it is LSTM or GRU, whatever it is. So to inference, to run the inference, if you see, the generate text will have parameters like model start text from where you want to generate, word to index and index to word, basically your vocabularies mapping. Okay, so those all are provided, and finally your story is generated. So what we are doing here is, first we are preparing the data set. The story is already here. We are preparing the data set, and then the model type is here, LSTM. We are training and saving the model. The model is already there. If you want, you can comment this out, and then you can load the model again. But yeah, we are doing it at single time, so I've just commented it. So once you're starting the inference, we can start it as once upon a time, and then we'll run the inference where I need to generate 50 tokens after that. Okay, so let's do that. Python 2 underscore intermediate RNN nets story.py. So here, if you remember, we are training it for 25 epochs. Okay, so it will soon show here. Here you can see it is, coming down. So yeah, here you can see once upon a time, there like it is trying to say something, like if I train it for even longer time, let's say 50 epochs, it'll be even better. Okay, but this is how you'll make a story generator RNN. In the next section of prerequisites, we'll see about neural machine translation with the advanced section, where we'll see how to use encoder decoder along with attention mechanism. That will be our next section. So yeah guys, I hope you all like this video. If you all like this video, please hit the like button, share it with your friends. If you haven't subscribed to the channel, please hit the subscribe button, hit the bell icon. I'll see you all in the next video. Until then, happy learning.